In the Ice and Rain series of lessons, we will examine the methods used to detect when an aircraft is flying in icing conditions. And we will look at the various systems that can be fitted to aircraft to prevent ice and rain becoming a problem. We will not be discussing pre-flight ground de-icing. This is covered in the Operational Procedures series of lessons. In this lesson, we will first quickly look at how ice forms, and then we will look at the various systems that can be used to detect icing conditions and give a warning to the pilot. Icing on aircraft in flight is caused primarily by the presence of supercooled water droplets in the atmosphere. If the droplets impinge on the forward-facing surfaces of an aircraft, they freeze and cause a build-up of ice, which may seriously damage the aerodynamic properties of the aircraft. These droplets can exist in the temperature band from 0 to -40 degrees Celsius. Below -40, they are already frozen and will not stick to the surface of the aircraft. The actual amount and shape of the ice buildup depends on the surface temperature and the size of the droplets. A full explanation of icing conditions is given in the Meteorology series of lessons. You should expect ice to be a problem whenever the temperature is between 0 and -40 degrees Celsius, and visible moisture in the form of clouds or rain is present. Ice detection systems can be split into two groups: those which sense a build-up of ice, known as accretion-type systems, and those which sense, by measuring temperature and humidity, when icing conditions are present. These are known as inferential-type systems. The simplest of the accretion-type detectors is the pilot's eye. He may be able to see ice beginning to build up on such things as the leading edges of the windscreen wiper blades. Some aircraft may have lights to illuminate the wing and fin leading edges, plus the engine intakes to help the pilot monitor for the build-up of ice at night. On some aircraft, the pilot's eye is the only ice detection system. To assist the pilot, some aircraft have a device known as the Teddington Ice Detector. This detector consists of an aerofoil-shaped mast protruding into the airflow, which is visible from the cockpit. The mast incorporates a heater element and a light to illuminate the mast at night. When icing conditions are encountered in flight, with the heater power supply switched off, ice accumulates on the mast and gives a direct visual indication of ice accretion. The heater may be switched on for a short period to dissipate accumulated ice. The more quickly the ice reforms, the more severe are the icing conditions. The Smith's ice detector is another accretion type of detector. It consists of a hollow tube, attached to the aircraft by one end, sitting in the airflow. It has holes drilled in the leading and trailing faces. There are 4 holes in the leading edge and 2 in the trailing edge. In flight, under normal conditions, the air enters the 4 front holes more quickly than it can exit by the rear 2. This causes a pressure build-up in the tube, which is sensed by a capsule connected to its base. The capsule expands, keeping a pair of electrical contacts apart. In icing conditions, the leading edge holes become blocked by ice, and the pressure in the tube falls. The capsule contracts, causing the ice warning light to illuminate. There is a heater element fitted around the tube to melt accumulated ice. Once again, the more quickly the ice reforms, the more severe are the icing conditions. The English electric or Napier ice detector is a mechanically operated accretion type of detector. In this detector, a serrated rotor shaft is continuously driven by an electric motor. The shaft rotates adjacent to a fixed knife edge cutter, with a clearance between them of less than 0.02 of an inch. The unit is mounted on flexible mountings on the side of the aircraft fuselage, with the rotor shaft protruding into the airflow, with its axis at right angles to the airflow. The cutter is in the lee of the shaft. Under normal conditions, little torque is required to drive the rotor. In icing conditions, ice builds up on the rotor and is shaved off by the cutter. Shaving off the ice requires greater rotational torque and causes the motor to rotate slightly in its flexible mountings. This movement operates a microswitch which gives an ice warning. The warning remains as long as ice continues to foul the cutter blade. The Rosemount ice detector is another mechanically operated accretion type of detector. It consists of a short cylindrical probe positioned in the airflow, mounted on a vibrator housing, which vibrates the probe axially. If ice spills up on the probe, the added mass reduces the frequency of the vibrations. When the frequency falls to a predetermined level, an ice warning is given. When the ice warning is given, a built-in heater element heats the probe, which melts the accumulated ice, allowing the vibrating frequency to return to normal and the warning to stop. After 6 seconds, the heater switches off and the icing cycle recommences. The frequency of the cycle may be measured to give an indication of the ice accretion rate. The final accretion type of ice detector that we want to look at is the beta particle detector. This is the most modern type of detector. It has no moving parts. The detector consists of 2 probes, mounted perpendicularly from the forward fuselage. The forward probe is an emitter, which emits beta particles. The rear probe is a beta particle detector, which detects the level of particle transmission from the front probe. Beta particles are absorbed by ice, so that, in icing conditions, fewer particles are sensed by the detector. At a certain beta particle count rate, corresponding to approximately 0.4 mm of ice, a relay in the detector probe will operate, causing a warning on the flight deck. Ice can only be formed when there is a combination of moisture and freezing temperatures. In the Sangamo Western ice detector, these 2 conditions are detected separately, and therefore icing conditions are detected rather than actual ice formation. This, then, is an inferential type of ice detector. The system comprises 3 main components: a moisture sensing head, a moisture detector controller, and a thermal switch. The moisture sensing head consists of 2 heated metal resistance bulbs situated in the airflow, and arranged so that the leading bulb screens the rear one, in such a way that no moisture impinges upon it. When the detector encounters moisture in the airflow, the shielded rear bulb remains dry and cools at a slower rate than the wet leading bulb. The moisture detector controller is situated in the base of the unit and senses the temperature difference between the wet and dry sensing bulbs. When the temperature difference reaches a predetermined value, it will send an icing conditions signal. The thermal switch is a contact operating thermometer which is housed in a bulb and is exposed to ambient temperature. With a temperature below freezing, the thermal switch will send an icing signal. If both the moisture detector controller and the thermal switch are sensing icing conditions, then an ice warning will be given, or the automatic anti-icing or de-icing cycles will be initiated. That is the end of the lesson on ice detection. You have seen that there are two types of ice detector. The accretion type, which senses actual ice buildup, and the inferential type, which senses when the aircraft is in environmental conditions where icing will occur. You will find that on many modern aircraft there is no ice warning system, or perhaps just the Teddington type of visual indicator. So an awareness of the in-flight conditions with regard to temperature and moisture is essential for all aircrew. In icing conditions, the first signs of ice buildup can usually be spotted on aerials or on the windscreen wipers. In this introductory lesson to ice protection systems, we will list the systems and components that need to be protected from ice and rain, and we will list the protection methods used. In the following lessons, we will discuss the various protection systems in greater detail. The following systems and components need to be protected from ice and rain. The engine air intakes and compressor inlet guide vanes need to be protected, as do the wing leading edges, along with slats if they are fitted. On some, but not all aircraft types, the fin and tailplane leading edges are also protected. Propellers can suffer from icing and need protection. Waste-water outlets and water lines in unheated parts of the fuselage will freeze up in flight any time the temperature is below zero, so they need to be heated. Any probes sticking out into the airflow, such as pitot heads and alpha probes, are susceptible to icing and need to be protected. These small components are usually electrically heated. Finally, cockpit windows need to be protected from both ice and rain. Ice protection systems normally use one of two different approaches to the problem. They are de-icing, where ice is allowed to accumulate prior to being removed, and anti-icing, where the object is to prevent ice from forming. The methods used for ice protection can be split into three groups. They are mechanical, using expanding rubber boots; thermal, with the heat being supplied by electricity, engine oil, or hot air; and liquid, using freezing point depressant fluids. These methods are all examined in detail in the following lessons. That is the end of the lesson. You should now know which surfaces need ice protection. You should know that de-icing involves removing ice that has built up, and that anti-icing is used to prevent the formation of ice. In this lesson, we will look at a mechanical ice protection system, as used on the ATR 72 shown here. A mechanical system, using pneumatically inflated boots, may be employed on the wing and tail leading edges of certain types of piston engine and some modern turbopropeller aircraft. This type of system is used for de-icing. It removes ice that has already formed on the surface. It is switched on when there is an ice buildup of between 0.5 and 1.5 centimeters, depending on aircraft type. The de-icing boots, or overshoes, which are fixed to the leading edges of the surfaces to be protected, consist of layers of natural rubber and rubberized fabric, between which are fitted flat inflatable tubes closed at one end. The tubes are also made of rubberized fabric. In some boots, the tubes are so arranged that when the boots are in a position on a wing or tail leading edge, the tubes run along the leading edge. In others, they run across at 90 degrees to the leading edge. The boots may be attached to a leading edge either by screw fasteners or by cementing them directly to the inboard portion of the leading edge, where the wings are thickest. The tubes in the boot sections are inflated with air from the aircraft's compressed air system. This air may come from the pressure side of an engine-driven vacuum pump, from a high-pressure reservoir, or, in the case of some types of turbopropeller aircraft, from the engine compressor. The inflation weakens the bond between the ice and the boot surfaces, causing the ice to break away. At the end of an inflation stage of the operating sequence, and whenever the system is switched off, the air is sucked from the boots to hold them flush with the leading edge. The suction may be produced by a vacuum pump or by Venturi action. This inflation and deflation cycle is repeated during the period the system is in operation. When the system is switched off, suction is applied continually to all tubes of the boot sections to hold the sections flat against the leading edges, thus minimizing aerodynamic drag. This type of system has two drawbacks. Firstly, the boots disturb the airflow over the leading edge, increasing drag. And secondly, they are quite expensive to maintain, as the boots wear out relatively quickly and they are easily damaged and eroded. The de-icer boots are pulsated in a set cycle, the frequency of which can be varied by a frequency selector to cater for light or heavy icing conditions. To reduce the volume of pressurizing air required, the boots are usually divided into groups. For instance, Group 1 may be the port and starboard wing outboard boots. Group 2, the port and starboard wing inboard boots. And Group 3, the fin and tailplane boots. When the system is switched on, the boots will inflate and deflate in sequence. First Group 1, then Group 2, and finally Group 3. At the end of the cycle, there will be a time delay, which can be varied by the pilot, depending on the severity of the icing before the cycle starts again. The controls and indicators required for the operation of the system vary from aircraft to aircraft. In the basic arrangement, there will be a main on-off switch and a selector to allow the pilot to select the time between cycles, depending on the severity of the icing. There may also be pressure and vacuum gauges or indicating lights to confirm system operation. That is the end of the lesson. You should now understand that a mechanical system using pneumatically inflated boots is often used on modern turbopropeller aircraft. You should know that it can only be used for de-icing purposes. You should also know that the two disadvantages of this type of system are that it is expensive to maintain and that it causes an increase in drag. In this lesson, we will look at thermal ice protection systems, as used on many turbojet aeroplanes, including the Boeing 737. A thermal ice protection system is one where the surfaces to be protected are heated. One major advantage of the system over mechanical systems is that there is no change in the profile of the surface being protected. This heat may be provided by hot air, electricity, or hot oil, although this method is rarely used. The most common method of thermal ice protection is the hot air system. There are several methods by which the heated air can be supplied, and these include the bleeding of air from a turbine engine compressor, the heating of ram air by passing it through a heat exchanger located in an engine exhaust gas system, and the heating of ram air by a combustion heater. The areas normally protected by a thermal system include the engine air intakes and compressor inlet guide vanes, plus the wing leading edges and slats if they are fitted. On some, but not all aircraft types, the tailplane and fin leading edges are also protected. In systems supplied with compressor bleed air, the hot air is tapped directly from the engine compressors. The air is normally taken from a low compressor stage and a high stage to ensure the temperature and pressure is sufficient at all engine speeds. The amount of air tapped off is a very small proportion of the total airflow through the compressor, so the effect on engine thrust output of using compressor air for ice protection is similarly very small. The bleed air temperature may be controlled by a pre-cooler using fan air before it passes into a bleed air manifold. From here, the air supply to the areas requiring ice protection is controlled by shut-off valves. In some systems, these valves are able to modulate to maintain the air pressure within acceptable limits. The exhaust gas heat exchanger method of supplying warm air is employed in some types of aircraft powered by turbo-propeller engines. The heat exchanger unit is positioned so that exhaust gases can be diverted to pass between tubes through which outside air enters the main supply ducts. The outlet temperature is usually regulated by a device, such as a thermostatically controlled flap, fitted in the ducting between the exhaust unit and the heat exchanger. In a combustion heating system, ram air is passed through a cylindrical jacket, enclosing a sealed chamber in which a fuel-air mixture is burned. The ram air is heated by contact with the chamber walls. Air for combustion is derived from a separate air intake and is supplied to the chamber by means of a blower. The combustion heater is fully explained in the pneumatic systems lesson. The hot air systems used for airframe ice protection on modern turbojet aircraft generally use engine bleed air and are normally anti-icing systems. In systems of this type, hot air is supplied to a pipe or duct running along the inside of the leading edge sections to be protected. These ducts are known as spray or piccolo tubes. The duct has spray holes in it, through which air is allowed to escape and heat the leading edge, melting any ice that has formed and preventing further ice formation. The air is then ducted rearwards before being dumped overboard through holes in the lower surface. The system is controlled by flight deck switches, which operate valves in the pneumatic manifold to shut off the airflow when ice protection is not required. Engine air intake de-icing or anti-icing can be achieved either using hot bleed air or an electrical resistance heating system. Electric heating is usually only found on propeller-driven aircraft, where the propeller is also de-iced by electric heat. On other types, electricity is usually only used to heat smaller components, such as windscreens and pitot heads, because of the high currents required. A typical hot air engine ice protection system is shown here. The air is tapped from the compressor at a suitable point. It passes through an electrically operated control valve, which is actuated by a switch on the flight deck. The air heats the inlet guide vanes, the nose cone, and the air intake cowl. The air is then exhausted either to atmosphere or back into the air intake. In an electrical heating system, heating elements, either of resistance wire or sprayed metal, are bonded to the air intake structure. The electrical power supply required for heating is normally a three-phase alternating current. In the electrical wire type of system, the elements are sandwiched between layers of glass cloth, impregnated with resin. In some systems, the elements may be sandwiched between layers of rubber. The outer surfaces are, in all cases, suitably protected against erosion by rain and the effect of oils and gases. In the sprayed metal system, a base insulator is brushed directly onto the surface to be protected, and then the electrically conductive metal is sprayed onto it. A further insulating layer is applied on top of this. The outer surface is then given a suitable protective coating. The resulting protected surface is known as a spray mat. In an electrically heated ice protection system, both anti-icing and de-icing techniques are employed. By using both continuously heated and intermittently heated elements. The system is controlled by switches on the flight deck. When the control switch is placed to on, the power supply is fed directly to the continuously heated elements and via a cyclic time switch unit to the intermittently heated elements. The cyclic time switch unit controls the application of current in selected time sequences, compatible with prevailing outside air temperature conditions and the severity of the icing. In this example, the output of the time switch can be changed by selecting either light or severe icing conditions. The cyclic circuit is arranged so that while the supply is on for some heaters, it is off to others, and vice versa, in order to maintain a constant de-icing load to the electrical system. A number of small components are electrically heated to prevent ice formation. These and the windscreens are the only items normally electrically heated on large turbojet-type aircraft. Some of them, such as pitot heads, angle of attack sensors, and temperature probes, may have switches and warning lights in the cockpit. Others, such as wastewater drain mast heaters and the inline heaters fitted to water pipes, operate whenever the aircraft's electrical system is powered. That is the end of the lesson on thermal ice protection. You now know that the heat source for thermal systems can be hot air, electrical power, or, very occasionally, hot engine oil. You should understand that airframe ice protection on modern turbojet aircraft is normally achieved using hot air bled from the engine compressors, with very little loss of engine thrust. These systems are usually anti-icing systems. You also now know that the engine intake can be heated using either hot air or electrical power. If hot air is used, the system will be an anti-icing system. But if electrical power is used, there will usually be a combination of de-icing and anti-icing. Finally, you should know that on turbojet aircraft, electrical power is normally only used to heat the windscreens and smaller surfaces and components. Short lesson. We will look at fluid-type airframe ice protection systems, as used on the Hawker 800 aircraft. A fluid or weeping wing system works on the principle of forming a film of glycol-based freezing point depressant fluid over the surfaces to be protected. This film of de-icing or freezing point depressant fluid combats ice formation by both melting the ice and by preventing adhesion of any ice crystals. Hence, the system can be operated in a de-icing or anti-icing mode. A typical system will contain a storage tank, a pump, and a network of pipes to transport the fluid to the required locations. The pipes terminate at distribution panels fitted along the leading edges of the surfaces to be protected. The distribution panels have porous outer panels on the leading edge of the aerofoil. The fluid is pumped into the cavity between the porous outer panel and a backing plate. It seeps out through the porous panel and is then distributed over the aerofoil surface by the airflow. The major drawback of this type of system is that the system's operation is limited by the amount of fluid in the storage tank. And, of course, the greater the amount of fluid carried, the greater is the weight penalty for carrying it. In this lesson, we will look at the various ice and rain protection systems available for aircraft windscreens. Windscreens are protected from icing by fluid sprays or by electrical heating. Cabin air may also be blown across them for demisting. Wipers and washers are also provided. And on some aircraft, these may be assisted by the use of rain repellent systems. We will now look at these systems in more detail. Independent two-speed wipers are usually provided for the pilots. They may be electrically or hydraulically powered and are controlled by switches on the flight deck. They normally have a parking facility. When the switch is placed to off, the wipers will park at the bottom of the screen. Windscreen wipers should not be operated on a dry windscreen. The windscreen washer system sprays washer fluid onto the windscreen panels and is used in conjunction with the wipers to clean the windscreens. A typical system consists of a fluid reservoir, an electrically driven pump, and pipes feeding the fluid to spray jets below the windscreens. A single washer button controls the fluid for both screens. There are two types of rain repellent system in common use. In one, the windscreen is given a permanent hydrophobic or water repellent coating during manufacture, which causes the water to form large beads and roll off the surface. In the other, a temporary fluid coating is applied to the screen when required. Rain repellent fluid should only be applied to the screen during very heavy rain. In a typical fluid rain repellent system, there will be a nozzle for each screen and a manifold which stores and distributes the fluid to the nozzles. The manifold is charged with repellent fluid from an aerosol-type disposable container which screws into it. Electrical time-controlled solenoid valves control the flow of fluid to the nozzles. Rain repellent fluid is sprayed onto the respective windscreen by momentarily pressing the rain repellent button switch on the captain's or first officer's wiper control panel. Each actuation of the switch opens the valve for a preset period of time, regardless of how long the switch is held in. The repellent reacts with the water, increasing the size of the water drops, which are then blown off the screen by the airflow. Depending on airspeed and rain intensity, each actuation should be adequate for 2 to 5 minutes of repellent action. Rain repellent fluid must not be applied to a dry windscreen, as it will reduce visibility. The method employed in a fluid windscreen de-icing system is to spray the windscreen panel with a methyl alcohol-based fluid, which will melt any ice that has formed. The principal components of the system are a fluid reservoir, a pump, which may be a hand-operated or electrically operated type, supply pipelines, and a spray tube unit. Here, we show a typical aircraft system in which fluid is supplied to the spray tubes by an electrically operated pump. Electrical windscreen heating systems are almost always anti-icing systems. Windscreen heat is used from takeoff until landing because the heat increases the flexibility of the screen and hence its resistance to damage from bird strikes. A heated windscreen is of a laminated construction. In the typical example shown here, the film-type resistance element is sandwiched between a hard glass outer coating and a thick clear vinyl panel or interlayer. There is another hard glass panel on the inside of the screen. There are two types of electrical windscreen heating systems in common use. One system has a temperature sensor attached to the windscreen, and the other has a temperature-sensitive switch. Both are controlled and monitored by cockpit switches and warning lights. In both types of system, the resistance element is heated by alternating current or AC supplied from the aircraft's electrical system. The power required for heating varies according to the size of the panel and the heat required to suit the operating conditions. Air from the air conditioning system can be blown across the inside of the screen for demisting purposes. In the system using a temperature sensor in the windscreen, the sensor sends temperature signals to an electronic controller. The controller varies the current flow to the windscreen to maintain it at a constant temperature. This is typically around 30 degrees Celsius in flight and a lower temperature, typically 16 degrees, on the ground. The changeover is made by the landing gear air-ground logic system. This system has the advantage of keeping the thermal gradient or temperature difference between the inside and outside of the screen to minimum, thus increasing the useful life of the screen. In the other system, temperature-sensitive switches or thermostats are fixed to the windscreen. When the screen reaches the required temperature, the thermostat opens, switching off power to the screen. When the screen cools again, the thermostat closes, reapplying power. In addition to the normal temperature control circuit, this type of system usually has incorporated in it a circuit which supplies more heating power under severe icing conditions when heat losses are high. When the higher power setting is selected, the supply is switched to a higher voltage output, thus maintaining the normal operating temperature. Both systems also have a thermostat in the windscreen for overheat protection. If the normal system fails to control the windscreen temperature, The overheat thermostat will cut off the power and put on a warning light. On some systems, the system will now operate in the overheat mode, with the overheat thermostat controlling the temperature and the warning light cycling on and off. On others, once the overheat thermostat opens, the warning light is locked on and heat can only be reapplied by cycling the control switch to off and then back to on. If the windscreen should overheat, then it may suffer permanent damage to the vinyl interlay. This will manifest itself as vinyl bubbling and discoloration. That is the end of the lesson. You have learned that windscreens can be protected from icing by fluid sprays or by electrical heating. Remember that electric heating of windscreens increases their impact resistance, so it is kept switched on from takeoff until landing. Remember also that cabin air may be blown across the windscreens for demisting purposes. You now know that wipers are used to clear rain from the screen. Remember that they should not be used on a dry windscreen. On some aircraft, the wipers may be assisted by the use of rain repellent systems. Bear in mind that rain repellent fluid should only be used in very heavy rain, and that it must not be used on a dry windscreen. In this lesson, we will look at how engine propellers are protected from the effects of icing. Ice formation on a propeller blade produces distortion to the aerofoil section, causing a loss in efficiency and possibly causing unbalance, which can lead to destructive vibration. The build-up of ice must be prevented, and this is usually done by electrically heating the propeller blades. Because of its thickness and lower speed, the inner third of the propeller blade is most susceptible to icing, and is always de-iced. In some installations, the middle third is also de-iced. The outer third of the blade is not so susceptible to icing, and is not normally de-iced. Depending on the type of aircraft, the electrical power for heating the elements is either direct or alternating current. These systems consume a relatively high amount of electrical power. However, they are controlled by employing a cyclic timer, which will de-ice the propeller blades of one engine at a time, thus reducing the power requirement. In some installations, a power relay is fitted in the engine nacelle. It allows the length of heavy high current wiring to be kept to a minimum, with light cable being used in the control circuit. In turbo-propeller engine installations, the propeller heating circuit may form part of a power unit de-icing and anti-icing system, with the cyclic control being integrated with the engine air intake heating circuit. The power required for heating is conveyed to the elements via cables, slip rings, and by brushes, contained within a brush block housing. Slip rings and brushes are components used to transfer electrical power from a stationary part to a rotating one. They are fully explained in the Electric System series of lessons. In icing conditions, during the unheated period, a thin film of ice will build up on the leading edges of the propeller blades. Before this film builds up sufficiently to interfere appreciably with the aerodynamic characteristics of the blades, the cyclic control applies heating power. The ice in contact with the blade surfaces melts, breaking the bond between the ice and propeller blade. The remaining ice is then carried away under the action of centrifugal and aerodynamic forces.